Hello again, physicists. Good to be back. So we're starting a new unit in class, and the name of that unit is Projectile Motion. Today is an introductory summation of what projectile motion is all about. Now, we will have at this point investigated an instance of projectile motion in class and drawn several of the conclusions that you're seeing in this video. So this is more for reinforcement and to give you an opportunity to do practice with the equations of projectile motion. So let's start with what a projectile actually is. To be a projectile, you need to be doing two things. Both things must be true for something to be a projectile. The first is it must be moving in a total of 2 dimensions. What that means is, you know from when we've been establishing coordinate systems in forces, we have the x direction and then we have the y direction as well. Well, if you're a projectile, this means that you are moving in both of these directions simultaneously, which will result in a curved path. Some examples of projectiles include anything involving sports, like a football or a basketball being thrown, munitions, things like a tank shell or a bullet being fired, and essentially anything that's being tossed with some sort of horizontal velocity at minimum. So these are all things that travel in 2 dimensions. Now, the second requirement is that to be considered a projectile, it needs to be something experiencing only a force of gravity, and no other forces are influencing it. This means that we are saying that air resistance is negligible when we talk about projectile motion. It's gravity and nothing else as far as forces go. We can then use principles that we learned in forces to determine what special characteristics projectile motion will have. Because the real big key to projectile motion is the fact that we can sort it into x direction motion and y direction motion. And there's one huge difference between those 2 motions. So to kind of hash out what is going on, I'm going to start by drawing a free body diagram for a projectile. So here I have a ball. I've established my coordinate system over here. And if I wanted to draw a free body diagram for the ball, by definition, a projectile is only under the influence of gravity. So my free body diagram would have the gravitational force exerted on the ball and then nothing else. I can then use Newton's second law to solve for what the acceleration would be. So if I plug in for F net, that would be just the gravitational force. And looking at my coordinate system, really this gravitational force is pointing in the negative y direction. So I'm going to make this a negative Fg. Next, we can do a substitution for Fg, because Fg is the mass in question, times little g, the acceleration due to gravity. And then this is what I would have. You'll notice that I have the same mass in the numerator and denominator, therefore they cancel, and I'm left with the acceleration of this projectile is equal to negative g, or negative 9.81 meters per second squared. And this is in the y direction. So we should probably make a note that this is the y direction, and that is what the acceleration is. A grand old negative 9.81 meters per second squared. Kind of like free fall. So we can think of the y direction of projectile motion being very similar to free fall. In the x direction, we can see that from the free body diagram, there are no forces acting in the x direction. That therefore means that the net force in Newton's second law would be 0, and that the acceleration, therefore, would be 0. So really the difference between x direction and y direction motion ties back to the forces acting on the projectile, therefore the acceleration of the projectile. So just as Galileo did hundreds of years ago, we're going to separate the motion of a projectile into x and y dimensions. And that's what this T-chart here is for. So make sure that you make something similar to this in your notes. So the big difference between the x and y direction is that in the x direction, again, the projectile experiences no net force. While in the y direction, the projectile is subject to a single force due to gravity. And next I'm going to write out what the consequences are due to that. So in the x direction, if there's no net force, that automatically tells us that the acceleration in the x direction is 0 meters per second squared. While the acceleration in the y direction, as we saw on the prior slide, will be negative 9.81 meters per second squared. The same acceleration that's true for objects in free fall. Keep in mind that the negative sign is just telling us that the direction is down. What would the kinematic graphs look like for each case? So in the x direction, a position time graph would be linear. And we saw that when we did our investigation in class. This would further mean that the velocity time graph would be constant, like that, because the x direction motion is, if we wanted to describe it, a motion of constant velocity. You got to remember that these two ideas are synonymous. If we have 0 acceleration, it's the same thing as saying we have a constant velocity. All right, let's look at the y direction. So if the acceleration is a constant number like that, it means that we have uniform accelerated motion, which would mean that our position time graph would be some sort of parabolic shape like that. And the velocity time graph would be some sort of linear plot like that. And then we could find that acceleration by taking the slope of the velocity time graph. Now, this again is what we would call uniform accelerated motion because the object is accelerating and it's doing so at a consistent rate of negative 9.81 meters per second squared. With this newfound knowledge about what's true with acceleration in the x and y directions, we can go a step further. We can then apply those rules to the big three kinematic equations we had from our first unit, and I've listed those three equations at the top here. And we can then have specific equations that will be useful when we're trying to solve projectile motion problems. I'm going to begin with the x direction and then apply the same three equations to the y direction. The only difference here will again be what is being plugged in for the acceleration in each case. With the x direction, beginning with my first formula here, the velocity squared being equal to the initial velocity squared plus 2 times the acceleration times the displacement of the object. In the x direction, since the acceleration is 0, that would mean that I would be plugging in 0 to this term, and the outcome would be basically this. That the velocity at any point in time in the x direction squared will be equal to the initial velocity in the x direction squared. I could go a step further and take the square root of both sides, and I would get this, which basically says the initial velocity in the x direction at any point is equal to the velocity in the x direction. Basically, it's telling you that it's moving at a constant velocity. This is kind of like no duh. This really isn't an equation. It's just a statement about what's true in the x direction. So our first kinematic equation actually will not be a part of x direction motion. All right, let's look at the second equation. So we have the velocity in the x direction would be equal to the initial velocity in the x direction plus the acceleration multiplied by time. Again, because there is no acceleration in the x direction, that would make this second term in the formula 0. And we're back to the same thing. Basically, that the velocity in the x direction is equal the whole time. Another no duh. Well, this is kind of boring. All right, let's look at the very last equation here. The displacement being equal to the initial velocity multiplied by time plus 1/2 the acceleration multiplied by time squared. Here we have this term that will again become 0 since the acceleration is 0 in the x direction, but we are left with something. We still have the displacement in the x direction being equal to the initial velocity in the x direction multiplied by time. Hooray! There is our one single equation that we will be able to use as far as the x direction goes when it comes to projectile motion. All right, let's switch gears and look at the y direction. This is going to be a little more interesting. Turns out all three equations get to stay. Every last one of them. Because in all three cases, we have a non-zero acceleration. So the y direction is definitely going to be a happening place to go when you are using your kinematic equations. So all three of these are fair game. Now there are a couple of things to note. There is crossover between the x and y direction, and I'm talking about time. Time is going to be the common thread that connects the x motion and the y motion, because time is not something that's spatially dependent. You know, I have time in my equation over here for x direction. That is the same time that is showing up here for the y direction of my projectile's motion. So if you're ever stuck on something in the x direction and it's related to time, know that you can go to the y direction and get that time and then go back. And vice versa works as well. So there are the four equations we can use for projectile motion. Last thing for today is I want to show you an example on how to solve a word problem involving projectile motion. The most basic projectile motion problem is what we call the off-the-cliff problem. This is a case where the projectile is being launched horizontally like so. Not at an angle, but just horizontally. And what that means is that in that case, all of the projectile's velocity initially is being projected only in the x direction. In other words, there is no initial y velocity, and therefore it'll be equal to 0 meters per second. So I have a description here involving a soccer ball. They've given us some information about the cliff and the landing point of the soccer ball. Our goal is to figure out what is the initial horizontal velocity of the ball. And if we wanted to translate that into some physics symbols, we're really looking for v naught in the x direction. So how are we going to solve this? Well, like I've been doing throughout the entire video, I'm going to separate the information given to me into x direction information and y direction information. And I'm going to make a list of what I know in each direction. Starting with the x direction, I know that the ball has traveled 35 meters in the x direction. So delta x in the x direction is 35 meters. If you want to think about it, think of the ball being launched horizontally off of the cliff, and they tell you that it lands 35 meters from the base of the cliff. So in my picture, this would be the displacement of the ball. And notice how it lines up with the x direction? That's why we're considering this an x given. What else do I know about the x direction? Well, I know that I'm trying to find the initial velocity in the x direction. And I don't know anything about the time, so that's kind of out of luck. But I do know that the acceleration in the x direction is 0 meters per second squared. It always is, because there are no forces acting on a projectile in the x direction. So there are all of my x givens. Let's now switch gears. Let's look at the y direction. What do I know in the y direction? I actually know a lot. I know since it's being launched horizontally, that automatically tells me that there is no initial velocity in the y direction. So v naught y would be 0 meters per second. I also know that the acceleration in the y direction is a negative 9.81 meters per second squared, because the only force acting on the ball is gravity in the y direction. Now, I still don't know time. So that is an unknown for both x and y. And the last thing that has been given to me is the fact that the height of the cliff is 22 meters. This is telling me that the ball is displacing itself from 22 meters above the ground to ground level. And that is going down, which would mean that the displacement of the ball in the y direction is going to be a negative 22 meters. Again, negative because the ball is traveling down. It's falling down. So there you have it, a complete table with all of the givens from this problem. Keep in mind that my information about the acceleration, that is what we call a hidden given. It is just something that is always going to be true for projectile motion. The fact that the initial velocity in the y direction is 0 comes from the fact that, again, this is being horizontally launched. This will only be true when a projectile is being launched horizontally. Now, how are we actually going to get our answer? Keep in mind that we're looking for the initial velocity in the x direction. So I'm going to have to use my one equation from the x direction. The displacement in the x direction being equal to the initial velocity in the x direction multiplied by time. I know what this is. It's 35 meters, but I do not know my initial velocity, and I do not know how much time it is spending in the air. When you encounter a problem like this, where you're stuck in the x direction, you have to switch to the y direction, because don't forget, time is both in the x and the y direction. I can use the y direction to figure out the time and then work backwards to figure out my initial velocity here. So I'm going to use an equation from the y direction to figure out what the time is. Based on what I know, the initial velocity, the acceleration, time, and the displacement in the y direction, it looks like this equation will be the one to choose. And then I can go about solving for the time in this case. Now it's important to keep in mind that the initial velocity in the y direction, this guy right here, is 0. So that is going to make this entire term 0. So that pretty much leaves me with the following. I would have the displacement in the y direction being equal to this far term over here. I can then rearrange that algebraically to get what the time is in terms of things that I actually know. And it would turn out that the time is going to be equal to the square root of 2 times the displacement in the y direction divided by the acceleration due to gravity. And in this case, that means that the time is going to come out to right around 2.1 seconds. We can then use that time to go backwards and plug it in up here in my original formula that I had. So the last step would be to solve for v naught x. So the displacement in the x direction was 35 meters, and that's going to be equal to the initial velocity in the x direction multiplied by the 2.1 seconds that I found when I was using the y direction. And that will lead to an initial velocity in the x direction of approximately 16 meters per second. There is my solution. So again, a couple things to rehash here. Initial velocity in the y direction is 0. Why? Because it was launched horizontally this time. Thing number 2, don't forget about what is always given as far as projectile motion goes with the accelerations in the x and y direction. And then lastly, when you're stuck in one dimension, switch to the other one because it's going to give you some helpful information to ultimately solve the problem. That's all I have for today. In class tomorrow, we're going to spend some time practicing using these concepts to solve word problems. And then we're going to move on to looking at cases where something is not being launched horizontally as a projectile. So until next time, physicists, until next time.